Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing with a look into molecules that possess a carbon double bond to nitrogen. The synthesis of imine-like molecules. Now, the last scribblecast lecture, we actually looked at the formation of imines and enamines, and we closed with a comment on a comparison between molecules that are imines, such as this molecule, for example, versus molecules that have a more electronegative atom attached to the nitrogen of the C double bond N. For example, we looked at replacing the CH3 with an NH2 group. Now, what's interesting about this is the nitrogen of the NH2 group is more electronegative than the carbon. Carbon is less electronegative than the nitrogen. The more electronegative nitrogen withdraws electron density from the nitrogen of the C double bond N. This increases the positive charge, basically causing the electronegativity of this nitrogen to increase. The effect is that the orbital shrinks that holds the lone pair. It's pulled in by the greater electronegativity of the atom. As a result, it's more stable unprotonated. It's less basic. It's less likely to pick up a proton. The first step in hydrolysis, if you remember the mechanism in the reaction of water and converting this back, was protonation. However, if you make this step less likely, then the equilibrium will lie more to this unit, the C double bond N, and protonation becomes less likely. Hydrolysis becomes less possible. And in fact, these molecules with electronegative groups off of the C double bond N's nitrogen, molecules of this type do not undergo hydrolysis as readily. So it's very important that we take a quick look at some of these molecules and how they're made. Now, because they are similar to imines in structure, they all follow the same mechanism of the imine itself. However, since they are less easily protonated, these molecules that attack the aldehydes and ketones can be reacted at lower pH conditions. Let's try, as a first example, the reaction between benzaldehyde. So here we have benzaldehyde, and we're going to react it with a reagent called hydroxylamine. Now, often we react these reagents, these amine reagents, as hydrochlorides, and so we have to deprotonate and free up the hydroxylamine. But we'll take a close look at that once we've looked at all of these reactions. Hydroxylamine will follow the exact same reaction mechanism we covered in imine reactions. It'll just be able to do it at lower pHs, and it will, of course, release a water molecule. The water molecule contains the oxygen of the C double bond O, and hence we've replaced the C double bond O with a C double bond N. The only difference now, and the only reason this is not referred to as an imine, is the OH group off the nitrogen. So let's name these. The original starting molecule was benzaldehyde. The reagent is hydroxylamine. All one word. And because of the hydroxy group, the product is referred to as an oxime. An oxime. We still call it benzaldehyde. Space, separate word, oxime. Hence, in order to be able to name these molecules, I have to remember that hydroxylamines produce oximes. And I have to also be able to recognize that this is a benzaldehyde. What I would do on scrap paper, of course, is I would draw, if I was asked to name this molecule, I would draw the aromatic ring, the C, the H, but I'd replace the NOH with a double bond O, and I'd name this molecule. Once named, I would add the word oxime because of the presence of the NOH group. So these are the oxime functional groups, oximes. And oximes are formed by hydroxylamine reaction with aldehydes and ketones. Let's take a look at how the NH2 group is formed, or look at the reaction of aldehydes and ketones with the molecule hydrazine. Hydrazine reacts to make what is called a hydrazone. So we have hydrazones. I'm going to use acetone, a ketone this time, as my example. If I react acetone with H2NNH2, this molecule is hydrazine. So we're reacting hydrazine with acetone. Again, water is kicked out, removing the oxygen of the C double bond O. And we produce CH3, C, CH3, double bond from the C to an N, and off of that end is an NH2. This molecule is a hydrazone, and so this molecule would be named as acetone hydrazone. Now, of course, you do the same thing if you were given this molecule to name, and I was a bit confused or thrown off by the presence of C double bond N. Simply recognize when it's an NNH2 you have a hydrazone. You have to memorize that. But note that if I draw this molecule and replace the NNH2 with an oxygen, it's very easy to name this guy. That's acetone. So you do that on scrap paper. Once you've got the identity of the aldehyde or ketone, it's easy to name, acetone hydrazone. Phenylhydrazones are formed by reaction with phenylhydrazine. So phenylhydrazones are prepared by reaction with phenylhydrazine. Now, we can take a molecule like diphenylketone. Do you recall the IUPAC name of diphenylketone? The IUPAC name is benzophenone. In actual fact, benzophenone was an alternative common name that was adopted by IUPAC. Benzophenone. And we react this with reagent H2N NH, but off of the H, of course, the NH is a aromatic phenyl group. This is phenylhydrazine. All one word. Phenylhydrazine reacts to give us water plus, let's draw this molecule. I'm drawing it at an angle, I'm drawing it small. Let's see if I can improve this. Now I called this molecule diphenylketone, I called this molecule benzophenone. Could I name this as phenylhydrazone, as benzophenone phenylhydrazone, or diphenylketone phenylhydrazone? Both names would be acceptable. Benzophenone phenylhydrazone. Ooh, and he's run out of room. Okay, well, let's try to make more room. Try it again. 2 words. I got it on. There. Benzophenone phenylhydrazone. Okay, and we can continue with the phenylhydrazine even in a more modified derivative called 2,4 dinitrophenylhydrazones. Two,4 dinitrophenylhydrazones. Let's take this molecule, methylphenylketone. Do you remember the IUPAC name for methylphenylketone? It is acetophenone. Acetophenone. So we've got methylphenylketone, and we are reacting this with this molecule. A phenylhydrazine. Okay. But off of, if we number this 1, we go 1, 2. There's a nitro group here. NO2 is a nitro group. 3, 4, and a nitro group here. So this is a 2,4 dinitrophenylhydrazine, all one word. Let's write that out. 2,4 dinitro phenylhydrazine. We react that. We once again get water. And we get phenyl. C double bond N, CH3. We get an NH. And off of that NH we have our aromatic ring with a nitro here, O2N, and a nitro here, NO2. Now, based on acetophenone, this would be called, big name, acetophenone space 2,4 dinitro phenylhydrazone. Try not to get the name of the reagent. Name of reagent mixed up with the product. 2,4-dinitrophenylhydrazine gives a 2,4-dinitrophenylhydrazone. The last one we want to look at is the formation of semicarbazones. Semicarbazones. Semicarbazones, I'm going to use benzaldehyde again. Semicarbazones are formed by reaction with semicarbazide. What is semicarbazide? Well, we have an NH2 attached to an NH. Off of the NH is a C double bond O, and off of the C double bond O is an NH2. The reactive nitrogen is the NH2 that's not connected to the carbonyl. This molecule is referred to as semicarbazide. If you take semicarbazide, react it with the molecule benzaldehyde, you can lose water, and you will produce benzaldehyde. Oops. So there's my benzaldehyde molecule. And you will have the N and NH, C double bond O, NH2. And this is benzaldehyde. Semicarbazone. All right. Now, oximes, hydrazones, phenylhydrazones, 2,4-dinitrophenylhydrazones, and semicarbazones all have been used in the identification of unknown aldehydes and ketones. The reason for this is they tend to form very crystalline products. They have very characteristic melting points. For example, the 2,4-dinitrophenylhydrazones are often bright red or orange in color, and they crystallize very readily. Now, this type of identification of aldehydes and ketones has given way to more modern spectroscopic techniques. The other point I want to make is that typically the reagents are handled as hydrochloride salts. For example, in the first oxime we used hydroxylamine, but more often than not, the reagent that actually weighed out is the protonated version of hydroxylamine called hydroxylamine hydrochloride. This is hydroxylamine space hydrochloride. Now, if you take hydroxylamine hydrochloride and you react it with a common weak base such as sodium acetate or sodium ethanoate, the ethanoate base will grab the proton, and you'll get your hydroxylamine, the H2N reagent that you need, plus acetic acid. And then the hydroxylamine can go on and react. You also get from this reaction sodium chloride. So it is often easier to weigh a more crystalline hydroxylamine hydrochloride, utilize it, deprotonate it to generate your reagent. And this is often done in all of the reagents from hydroxylamine right through to semicarbazide. Okay, we're going to move on now and take a look at a very unique reaction. A reaction in which you were able to form alkenes from carbonyl compounds, aldehydes and ketones. The reaction is referred to as the Wittig reaction. Now, the Wittig reaction is very interesting because it involves the use of and formation of phosphonium, sounds like a phosphorus is involved there, ylids, phosphonium ylids. And this is a new word, ylid. What is an ylid? What is a phosphonium ylid? Well, first we have to know what ylids are. Ylids are based on the term Zwitter ion. Do you recall what a Zwitter ion is? If you said a Zwitter ion is a molecule that possesses a positive and negative charge, overall it's neutral, but there is a distinct plus and a distinct minus in the molecule, you're correct. A Zwitter ion is a dipolar ion. It possesses both positive and negative charges in the same molecule. Well, ylid is a special type of Zwitter ion. If the Zwitter ions, positive and negative charge, are adjacent, you're an ylid. Ylids, the plus and the minus are adjacent. If they are not adjacent, you call it a betaine. A betaine is a Zwitter ion in which the plus and the minus are non-adjacent. Non-adjacent. Okay. All right. How do you prepare phosphonium ylids? Well, because the reaction proceeds through an SN2, the preparation of phosphonium ylids only works. The preparation of phosphonium ylids will only work when you react a phosphine with a primary, well, I guess methyl, primary, secondary alkyl halide. This sounds an awful lot like we're seeing an SN2. Are we getting an SN2 reaction here? Let's take a look at the reaction mechanism for the formation of the phosphonium ylide. So, the phosphine that we're going to use is triphenylphosphine. 3 phenyl groups. I'll draw it this time, but after this I'll just refer to it as C6H5 3 times. Triphenylphosphine has 3 phenols off of it, so it's quite bulky, and a lone pair. We can use this, and in order to show a full SN2, I'm going to use a chiral alkyl halide. So I'm going to use an H here, CH3 here, CH2, CH3, Cl, okay. And the phosphine is a powerful nucleophile. Remember, as you go down in a group, nucleophilicity increases, and phosphorus is right below nitrogen, so it's a more powerful nucleophile than nitrogen. It does backside attack, you kick out chloride, and you get inversion. And so what you produce is a phosphonium ion. A P. And then we have the C with the H, the CH3, CH2, CH3. And so we got inversion of the chiral center, and now there's a large positive on the phosphorus. Now, this is not an ylide. Clearly, we do not have a plus-minus charge. One of the reasons you don't go beyond secondary is not only the fact that you can't do the SN2, but also the fact we need a hydrogen to deprotonate to create our negative charge. And so we have to treat this with a powerful base. The base we often use could be sodium ethoxide, an alkoxide base, O minus, CH2, CH3, you could use propoxide, butoxide. So you can use any alkoxide base, or you can even use the more powerful bases, the alkyl lithiums, such as lithium, or with the butane, or butyl group, that is butyl lithium. CH2, 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 CH3. Either of these are capable of pulling a proton off of this carbon that's adjacent to the positive charge. The proton removed with ethoxide would give you ethanol. Removing the proton with butyllithium would give you butane gas that would bubble out of solution. So you can use either of these. So it should be nowhere there. Of course, what you get then is your phosphorus with its 3 aromatic rings. But now, so still plus on the phosphorus, and we still have our CH3 now, our CH2 coming out of the board, CH2, CH3, and our lone pair where the proton was. There's a lone pair. And the carbon is now negatively charged. And hence we have a zwitterion, a minus and positive. But not just any zwitterion. The minus and positives are adjacent atoms, so it's called an ylid. Because it's a phosphonium ion, positive phosphorus is called phosphonium, it's called a phosphonium ylid. Now, why would this deprotonation occur quite readily? Well, it is resonance stabilized. I can dump these 2 electrons towards phosphorus, and I can make a phosphorus P double bond C. Carbon will go sp squared hybridized. And phosphorus will have its 3 aromatic rings. Three aromatic rings. So the phosphonium ylid is quite basic, loses a proton fairly readily because it is resonance stabilized. You will note that phosphorus can have a double bond to it, 10 electrons here, because phosphorus is in the 3rd row. It has empty d orbitals into which the electrons can be placed. This would not work if we replace phosphorus with nitrogen. First off, nitrogen is a smaller atom, and with the bulky group's backside attack on the secondary would become difficult. Also, secondly, nitrogen is less nucleophilic than phosphorus. But more importantly, if we went all the way through, replacing nitrogen all the way through, there is no way I could draw this resonance contributor, because nitrogen with 10 electrons around it is a violation of the octet rule. Nitrogen's in the 2nd period, and there is no such thing as 2d orbitals into which you can dump electrons. So this is why we use phosphorus triphenylphosphane and why we prepare phosphonium ylid. Okay, now phosphonium ylid is simply the reagent. This molecule with phosphorus right here is our key reagent. Now, let's take a different phosphonium ylid and observe, a more symmetrical one, what happens when you react it with the ketone or an aldehyde. Let's try the molecule ethanal. What happens if I take CH3, C double bond O, H, and react it with a phosphonium ylid? P. Looks like I've decided to draw phenols all the time. And let's use one that's not chiral. And let's draw it as the Ylid. So I'm going to have made it from isopropyl chloride, so I'll have this. What effectively happens when you do this reaction is that it looks like the oxygen and the carbon with the two methyls swap positions. That is, you finish up with an alkene where you replace the oxygen with the carbon with the two methyls. The oxygen ends up on the phosphorus. I'll write a short form, C6H5, 3 times P double bond O, and making a triphenylphosphine oxide. So the Wittig reaction is this is the Wittig, the phosphonium Ylide effectively puts a carbon on the C double bond, replacing it with the oxygen. Now, clearly, the question that really pops in your mind is, how does this happen? To answer that, we have to look at the reaction mechanism. Obviously, the reaction involves nucleophilic attack of the C minus, the lone pair on the C minus, and by the way, I may not have drawn it, but there is a lone pair here. The reaction of this on our aldehyde or ketone. Nucleophilic acyl addition. The minus attacks, the carbon. Pi electrons move out. And what you end up with when that happens is your P with 3 phenols off of it, so C6H5 3 times. Off of the P, which still has a positive charge, okay, which still has a positive charge, is a carbon, and the methyls are now pointing up and away. Fine. Attacks the C, and once it's done that, you get the O minus here. You can guess what's happening. The O minus gets attracted to the phosphorus plus, and because there's empty d orbitals, electrons can be dumped, and you can temporarily form a very strained four-membered ring. And with that, off the phosphorus, we still have our C6H5s, our phenols, 3 of them. But here we'll have 2 lone pairs, and we've lost a negative. Now, what can readily happen is a paracyclic movement of electrons Do you remember what a pericyclic movement of electrons means? It means electrons move in a circle. The phosphorus carbon electrons, the two electrons there, can go there, can shift in this direction to give you a pi bond between the phosphorus and double bond O. The carbon-oxygen bond can break, giving you two electrons shifting to make a carbon-carbon double bond. So the molecule can quickly fall apart, and if I draw it exactly as I have it here, so I'm going to just draw it down so you can see the positions, and I'll draw the carbons in the same way. They can leave like this. And lo and behold, notice my H had turned into methyl. I apologize about that. There we go. And that's an alkene. So once the pericyclic reaction is done, you've got your phosphine oxide and you've got this alkene. So it's fascinating that you can actually make an alkene from an aldehyde ketone, which effectively looks like you're just pulling off the oxygen and placing on a carbon with two other carbons attached to it. Amazing that you can replace a C double bond O and make an alkene. Now, interesting to note, and I'll just circle this in red, what kind of Zwitter ion is this guy? It is a Zwitter ion because there's a plus-minus charge, but notice if you consider bonds, the oxygen is not adjacent to the phosphorus. Yes, it wraps around and gets in close proximity, but by counting and looking at the bonds, the oxygen is not bonded next door to phosphorus. And because of that, that means the plus and minus are non-adjacent. So what kind of Zwitter ion is this? This is called a betaine. So you should know the definition of both betaine and ylid as well. Okay, well, that's another Scribblecast lecture that we've completed. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening. If you have any questions, don't hesitate to contact me. You can email me. My email address is bloyd@mhc.ab.ca. That's BLLOYD@mhc.ab.ca. Thank you very much.